I hope it's visible.
Yes, ma'am.
Okay.
Ma'am, it's for week 1 to 4 also.
It's for week 5 and 6. But if
Okay,
we are
ma'am.
left with some time at the end, we can discuss other weeks too.
Okay, ma'am.
So week 5 and 6 for now. So let's start with it. It's week 5, 6, the revision session. So starting off with the definitions are very basic. We just recall basic things. The first thing we have is a one-one function, which is also called an injective function. Injection. So, and to verify this, you have a test called horizontal line test.
Ma'am, we are
And
revising week 5 and 6.
sorry, what?
Ma'am, today we are revising 5 and 6.
Hello. Am I audible?
Yes, you are. There was somebody asking if it's the revision of week 5 and 6.
Yes, it's for week 5 and 6. It's the revision session for week 5, 6.
Ma'am, can you a little bit louder, ma'am?
This is the revision session for week 5, 6. We're starting with the very basics. We'll call some basic things from week 5 first, and then we'll go through some questions. Is that okay? Is that clear now?
Yes, ma'am.
So starting off with the definition. So I hope everyone knows what an injective function is. And if there's anything you have a doubt in the basics and all, you can ask it here. It's fine. And so for
Ma'am,
one
your voice
function,
is
you
very
have
low.
horizontal line test. And
Ma'am, your voice is very low. We are not able to hear it properly.
okay, wait, I'll just rejoin then. Wait. Hello, is it better now?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Just give me 1 second. Okay, so we were discussing the definition, the horizontal line test for one functions, and then we have for functions to verify if it's a function or not. For functions, we have vertical line test. So verify if it's a function or not. It's the same as this one, horizontal line test. And then what are the other ways to verify that if a function is 1, 1 or not? So 1, 1 verification. You have some ways to do it. So the first one is by looking at the graph of the function. Obviously, the horizontal line test. It is using the graph. And then the second one is by checking if your function is strictly increasing or decreasing. If your function is strictly increasing or decreasing, this implies that it is 1, 1, and not the other way around. It's a one-way result, this one. And then obviously the definition. You can use the definition of 1, 1 functions. So these are the three ways, major ways that you can use to verify if a function is 1, 1 or not. So let's just say, for example, we'll do some questions on this then. Let's just say you have this x squared plus 1. So you can use the very definition. Let's just say your function takes the same value at x and y. This is what it means, right? This is fx, and this is f. See if x and y turn out to be same or not. We can do this. This gives you xy equals 1. That means if you have y is equals to 1 by x and x as x, so if this is the thing, for these coordinates, you'll have, for these two things, you'll have the same value, right?
Ma'am, same value
Of f. That's what what we did here is we just took two arbitrary x and y and we equated the function's value at x and y. And then this is the condition that we are getting. So for this to be true, this should be true, right?
yes, ma'am.
Both ways. It goes both ways. This is an if and only if thing, right? So if, for example, if I take one, not one, if you take one, you'll get one, and then reciprocal of one is one as well. So let's just take 2.5. So if you take 2.5, you get the function's value to be same. This function will give the same value at 2.5. So this is not a 1, 1 function. So we did it by using the definition of 1, 1 functions. And then there are other ways. Let's just take another example, which is this x squared plus x to the power. It gives us this. We know that x squared, so if you want to check this thing, what happens here is, let's just say you want to check in the domain 0 to infinity. This is where your function's domain is. This is not the natural domain, obviously, but we're taking it to be this. We know that x squared is an increasing function. X to the power 5 is increasing, and x to the power 7 is increasing, right? All of these are increasing functions. So if you just add them up, this will be an increasing function. In fact, these are strictly increasing functions on this domain, only on this domain. This will be an increasing function too, right? Right, it's a 1, 1 function. These strictly increasing functions imply 1, 1, not monotonically increasing ones. So because this is a strictly increasing function, this is a 1, 1 function. Let's just say you change things here and you take the reciprocal of this.
Is there only integers in the domain?
Integers, yes, there are integers. There are integers in this set, right? there are integers in the domain.
No, ma'am, only integers or decimal also.
I can't hear you. Can you speak a little louder?
Ma'am, is there only integers or decimal numbers also?
This includes everything. 0 to infinity includes everything starting from 0 till infinity. That means till forever, starting from 0. Is that okay?
So, ma'am, for less than 1 and greater than 0, uh, there x to the power 5 and x to the power 7 be decreasing function.
Yeah, these all are, yeah, you're right. All of these are, let's just take one here. Is it fine now? This
Yes,
was
ma'am.
just an example to illustrate how you can just, if there is a function given and you see that all of them are increasing functions, then you can just conclude that this is a 1-1 function. To illustrate this thing, we did this. You can take, yeah, you're right. If you take it from 0 to 1, then all of these are decreasing. Then this will be a decreasing thing. But what matters here is, no, if you have 0 to 1, say, and then 1 to infinity. It doesn't matter from 0 to infinity, you can keep it 0 to infinity. Because from 0 to 1, it's from 0 to 1, you're getting, okay, if you take something from 0 to 1, no, this is a decreasing function like this. And then it's an increasing function afterwards. So you might
Yes,
be
ma'am.
worried that it might take values equal here. But the thing is that when you take, you will have to analyze this thing. If you have x from 0 to 1, then your x square and everything will be from in 0 to 1 only. But the sum can still exceed it, right? And if you'll have things from, you need to think about this in a little detail because you have this thing and if this is the function, say, it can still exceed 1 and if you take something, even if you take something very close to 1 point something, no, this still turns out to be a huge number. So it's very unlikely that these two will be, most likely this is something which will take a very small value, probably less than, so all of these can take 1, all of these are less than 1. So they can't take a value greater than 3, obviously. And about, but we can't still for sure say that they won't be same. So let's just take 1 to be 100% sure that this is going to be an increasing function and hence a 1. Is that okay now? And then next up we were discussing this thing. If you have something like this,
Excuse me, ma'am.
yes,
Ma'am, I think your voice is lagging.
okay, we can just, if I'll just go on for some time more and then if there's still a problem, is there a problem on your end or is everyone facing the same thing?
Ma'am, I think in the chat
I'm
box,
also having the same.
Okay. So I think can we just wait, see it for, observe it for 2 minutes and then if it's still lagging, then we can just, I'll try to figure something out. Is that okay? Is it still lagging though?
No, ma'am, for me it's not
no,
lagging
ma'am.
still.
Ma'am,
Not
it's
now, ma'am.
correct.
Okay. If you have something like this, what we were discussing here is if you have something like this, it becomes difficult because now this is an increasing function this is increasing and this becomes a decreasing function because, yeah, this is a decreasing function. So you can't actually use this same strategy here. Instead, what if this were the case, then you could. If this is it, now you can again use the same thing because this is increasing. This is an increasing thing. And now, okay, so if you have a function and it's increasing, and if you put a negative sign in front of it, it becomes decreasing, right? And if you take the reciprocal of it, it's still decreasing. And if you do both of them together, then it's still increasing, right?
Yes,
And
ma'am.
this is still increasing. The same thing with this one. So there are a lot of questions on this thing where there are increasing functions added or done something like this, where it still turns out to be increasing. Then we have another example. Let's just say you have where you can use the definition. You have this thing. Now you can't really tell by looking at it if it's a 1-1 function or not a 1-1 function, and you can't even tell if it's increasing or decreasing or if it's neither. So one way to do is you can obviously use the derivatives. Now that you're familiar with derivatives, you can use them here and verify if it's an increasing function or decreasing function. And the other way is the definition. So if
Ma'am, how does derivative show whether it is increasing or decreasing?
if this is your
If
function,
f dash x is greater than 0, then it will be increasing.
yeah,
And if
and
it's strictly increasing. If f dash x is greater than or equals to 0, it's increasing only.
Okay, greater than or equal to 0 is increasing and less than or equal to is decreasing.
yes.
It is strictly decreasing
Yeah,
and
it's
increasing.
strictly. So one way is to do this, but this derivative thing is not very easy here either. It will take time, and the definition will take time.
But,
Yes.
I mean, can I ask you a couple of more questions about derivatives, or we want to keep it for tomorrow?
Yeah, if you can just quickly.
Okay, so when we take a derivative, like an x square would end up giving a 2x, right, as a derivative. Yeah, but you still have an x component there, right? So how do you know if that's that's greater than 0 or not?
It
Unless
turns
you
out to be something very obvious like this. If it's obvious, otherwise you check things for intervals, right? So if you have something like x square plus 1 as derivative, then it's obviously greater than 0, or x square for that matter. So if these things are there, it's obviously greater than 0. If you have something else, let's just say x square plus x plus 1, then you can just check where it's greater than 0, where it's less than 0. So you'll get, is that fine? So that way you can know if it's,
okay, ma'am.
okay. You can just put that point here, in fact. So you know what's going on at that particular point. If this is the point A, then it's, and if this thing turns out to be 0, then greater than 0, then it's increasing here. It's something like this.
Okay, ma'am.
Otherwise, sometimes if it's an strictly increasing function, it's everywhere. If it's strictly increasing everywhere, this is what you're going to get in the derivative thing. Can we proceed with this question, or are there any other things?
Ma'am, can you repeat this once more?
The derivative one?
Yes, ma'am, the increasing and decreasing function.
So let's just say you have a function fx and you take the derivative of this. So if you just do this thing, if it turns out to be greater than 0, then that means at that particular point, if you have this point, that means it's something like this at this point. Is that okay?
Yes,
And
ma'am.
if you get a 0 here, it means you have something like straight So at that point, because it's just a point, it will be straight thing. It will take things as this, and here it's straight.
Ma'am, here what is the difference between f dash x and f dash a? Is they same or just the value?
They're same. This is a variable. This is a particular number, particular element in the domain.
So ma'am, when we put the value in the f dash x function, we'll have to see whether the function is greater than 0 or not after putting the value.
Yes, after putting the value, you have to check if it's greater than 0 or less than 0. Sometimes
Ma'am, in case we're not given the value, then will we be able to see whether the function is increasing or decreasing?
that's what I said. When a function is strictly increasing, you get something like, let's just say you get the derivative as e to the power x, then it's always increased. It's always positive. You don't even need to know the value of x. This function is always increasing, which means it was a strictly increasing function. You have this in the derivative, which will only be possible if the function itself is e to the power x. But still, if you have something which is obviously positive, then it's a strictly increasing function. You don't need to put values there.
Just like if we have a function as 3x square plus x cube, is this an increasing function?
You need to find out the derivative. And then if it
If
turns out
this
to be
is the
something,
derivative, if this is only the derivative,
this is the derivative. No, then it's not. See, there are values of x when this might be positive and this might be negative for other values. So it's not a strictly increasing. If this is the derivative, then whatever function's derivative this is not a strictly increasing or strictly decreasing function. In whole of R, it might be at some interval, it might be increasing or decreasing. Then you'll have to test the sign of this, right? Then you have to look for the signs of when this is positive, this whole thing, when this is negative.
ma'am, it means we have to find the roots which will make them positive.
Those are not called roots. Those are like solutions of this thing. Solutions of, let's just say this is fx is greater than 0. So yeah, you have to find that out by just. We've done this before when you have factors and we say either this is positive, or. But in this case, you're going to get a lot of factors. So it will become, you can just cancel some of it. There are redundant factors here.
Yes, ma'am. Yes, ma'am.
Be 3x. 5x minus remove the, let's just x here. We've removed the redundant factors. This just turns out to be this thing. So if you need to find now, you can't actually predict. Sometimes what happens is if this is an increasing function and this is a decreasing function, you can just say that this whole thing is an increasing thing. Is not, is that the case? This is not the case. Both of them are increasing, right? So you can't use that here. What you can do is you can just do it by definition. We've already done it. You just have to do this thing. Then when you solve for it, you'll get a condition at the end. Do I need to do this or can you guys try it on your own? Okay, let's just quickly do it then. It's 16y plus 5xy minus 6 minus 2x plus 15x minus 6 plus 5xy minus 5 is, here is You can
Is
obviously
this
see that this
is
equation
this a
is
doubt
not going
session?
to be consistent. No, this is a revision session. We're doing questions on this.
Is this
From
question is
here.
created by you or you are taking a doubt?
This is a revision session. We are doing revision for week 5 and 6, and we're doing questions on those weeks.
Okay.
Ma'am, we are
Then
doing
we have,
only week 5 and week 6.
yes, get a 15 and minus 2 thing, which is inconsistent. This is an inconsistent thing, which means that unless now you can cancel these two things. What we've done here is that we have cancelled these two factors. That you can do only when your y is not equals to x. So this just means now, since this is not possible, this just means that these two factors are, you can't cancel these two factors, which would mean that your y is actually equal to x. Otherwise, you could have cancelled it, right? Where y is x. Is that okay?
Yes, ma'am. Yes, ma'am.
This is the condition that you get at the end. And then we have other examples of minus e to the power x is a decreasing function. This one's a strictly decreasing function. Then let's just have it's going to be 1, right? And then let's just have a look at this one. You know that your tan is it's a function from minus 5/2 to 5/2. Right? And so your tan inverse will be from here. So you don't really need to check for this thing because it's obvious because it has an inverse. And you can just add one more thing because this thing has an inverse on R. That is why it's an increasing. It has to be a 1-1 function, right? Without it being a 1-1 function, it can't have an inverse. This is a 1-1 function. Is that all right? You can add one more thing to the
So
list of
anything which is any function which has got a inverse, that means the original function is a 1-1, is it?
yes. But if it's, let's just say there are conditions here. So you have to be very careful of the domain and 2 points. If your function is from say D to R, then if you have an F inverse from let's say R to D. So if this is the thing, then your function is 1-1 here on this thing. And in this case, you'll have to have the same things here, right?
Yeah.
Hello, ma'am.
No. Yes.
Hello.
Yes,
Ma'am,
you're
could you please
audible.
show the question once? Ma'am, could you please show the question once?
This is it.
Means what were you required to find out? Actually, I was disconnected.
We're trying to find ways to figure out if a function is 1-1 or not. So we've discussed 4 ways to do it. And then one
Ma'am,
of
could you please just
this
name
is
the 4 ways? By looking, I can understand, but could you please tell the 4 ways? Means what that?
one is the graphical way, if you can plot the graph.
Okay.
The other one is strictly increasing, decreasing, then the basic definition that you have. And then if it's a function is invertible, then wherever it's invertible, at that thing, this is going to be 1. So let's just say you have, so for example, you have, let's say x square. So x square is this thing. So now this function is obviously not 1-1, it's not invertible either, right? Because for invertibility, you need, so if you have an inverse, it's obviously invertible. If you have an inverse, it's obviously a 1-1 function because for the function to be invertible, you need it to be both 1-1 and also, right? So
Ma'am,
this is the
inverse of trigonometric functions.
yes, this is the inverse of trigonometry. But you have to be careful of where it is invertible. Because this one is invertible everywhere because it's the R thing here, right?
So, ma'am, it's not necessary that sine inverse is also an 1-1 function.
No, it's not a 1-1 function. We'll come to that in a while. We're discussing this thing. So if this is, let's just start with an easy example to understand. So if x square you have, then this is not invertible, neither it is 1-1, right? So, but if you take this thing, just now if you change the domain from 0 to infinity, now it's a 1-1 function and it's invertible too, right? And its inverse is this thing. So that's where when you say x squared inverse is root x, you need to specify that x squared inverse is root x on this domain only. Otherwise, it's not, right? So it's going to be 1-1 here only. I hope that's clear. So when you say that your f is from D to R and then your f inverse exists, that means on this thing, on the domain thing, it's a 1-1 thing. Is that okay? So, like a tan function. When you're talking about tan function, tan of x, it's 1-1 here. It's not, if you will keep the domain restricted to this part, it's 1. Similarly, tan inverse domain is this. So it's this one is 1-1 everywhere. Is that all right? Should I explain one more time or is it clear? Is it clear?
Ma'am, I have a doubt regarding week 6. Hello?
Yes, we'll just quickly go through week 5 and then we can take the doubt of week 6 because we're doing
Okay.
this in order. I don't want to disrupt the order. This is the thing. And then you have, let's just say, the tan inverse function, that example is clear to everyone, right?
Yes, ma'am.
Okay, and then you have this thing. Let's just say this is the function, then there are ways to do it, but the graphical ways, have we already done this? It's by the way, it's using definition only.
Ma'am, done what?
Because I think we've already done this in the beginning of the session, this example. And if we haven't, this is using the definition only. We've already done 2 questions using definition, and this is using the same approach. Same approach is to be used here. And graph, you can't plot of this. So graphical way we can't go. And then if there is anything, if there's a function given to you, let's just say, and you want to figure out the inverse of the, if it's 1-1 or not, then you can just simply try to figure out the inverse of it. Now there still are functions whose inverse you can't directly find, like this one. Let's just say you have this thing. Now, if you try to find the inverse of this the usual way, you won't be able to find it. If you try to write x in terms of y, you won't be able to write x as a function of y. This is not possible here. So you can't find the inverse of this. So that doesn't mean this necessarily does not have an inverse. So that's not the only way to find inverse. So all I'm trying to say is if you can find the inverse, well and good, that means it's an 1-1 function. This is what it means. But if you can't find it, you will have to make sure of some way to show that this is not an invertible function. Then only you can say, and even if it's not an invertible function, you can't really say if it's majorly because of, if you have taken care of the domain and codomain everything, then it's majorly because of 1-1ness. That means 1-1ness is missing. Not because you're taking, if you're taking care of the codomain, let's just say codomains are very, you can change them. Let's just say if you have a function e to the power, let's just say e to the power x function you're taking. So this function is from, now if you take it from here to here, and if you take this to be the codomain, this is not an invertible function. But if you change the codomain to say r plus, then it is an invertible function. That's what I'm talking about. These are like, you can change this thing. So if you can't find the inverse of something, if you're sure that the inverse does not exist, then it's most likely because it's not 1, 1. Because the codomain can be handled. Is that understood? All I'm trying to say is, if you're not able to find the inverse, just drop the inverse method. It doesn't say that it's not a 1, 1 function. You'll have to try some other
Ma'am,
way.
can you please repeat the R plus
And that is,
example? R plus example, can you please repeat?
if you have this function from R to R, this is, if you take this to be the codomain, then it's not an invertible function. You must have done this several times, that e to the power x is an invertible function and its inverse is natural log of x. But that's only true when your codomain of e to the power x is R plus. If you're taking the codomain to be R plus, because this is, look at the graph of e to the power x. So you don't have negative values here. So that means your negative values are not attained at
Got
any
it,
point. So
ma'am.
there's no x for which e to the power x is negative. So
Got
it's
it.
only invertible on R plus. So that's what you have to take care of. If you can't find the inverse of something, just drop the inverse method and try something else. Then we have this thing where, okay, we have this, let's just say we have a 1, 1 function. Can we say that it's a, if you have a 1, 1 function, say fx, can I say that it's an increasing function or a decreasing function? One of these. We know that if it's a
Yes.
strictly increasing function or a decreasing function, then this holds. Can we say the other way around? Can we say that this is true too? So this isn't true. Just in case you're asked strictly increasing or decreasing and you see that the function is 1, 1, it doesn't mean that it's increasing or decreasing. Forget about strictly increasing, decreasing. You can't say this thing. Now, if you get something like this, because you've already run continuity, so if you see something like this, a 1, 1 function and it's continuous too, then this means that it's either an increasing function or a decreasing function. So this is the counter example for this thing. Let's just say you have a 1, 1 function and you have to show that it's not an increasing. So let's just have this thing. And then this thing, and then let's just have this thing here. It's a, on this domain, it's a 1, 1 function, obviously. Right, every value is attained one time, but it's not an increasing or decreasing function. But if you just add one condition to it, that it has to be continuous. So if you're taking a function which is continuous and it's 1, 1, it has to be either increasing or decreasing. Is that okay, or should I just explain it using the graph?
Ma'am, can you explain it using a graph?
If there's a 1, 1 function, 1, 1 function means that you can't have, so if you, let's just say this is a continuous function. Let's just say you're going up. Either you, if you're, this is the start of your domain, either you go up and or you go down. Let's just take this. And for this to not be strict increasing or decreasing, you have to come back here. It's a continuous function. What we did earlier was we took this thing and then we come back like this. We can do it because it's not a continuous function. That's why we can lift our pen graphically if you look at it. So if you have till this point, then you, and there's no problem because it's not a condition. So this is still a 1, 1 function, and is that okay? But when you say
Ma'am, your
that
voice
you
broke.
have to increasing initially, and it's a continuous, is it fine now? If you have the simple logic is, if you have any, if you say that there's a 1, 1 function and it's continuous too, so that means it can't repeat values. So if it's a 1, 1 function and it's continuous too, so for it to repeat, if you do this thing, if let's just say this is not increasing, You started with this thing. If it's not an increasing function, then you have to come down. You have to do this thing. But if you do this thing, then it will violate the property of 1-1. The 1-1 property will be violated. And if you just lift your pen from here, if you're thinking of doing something like this here, then you'll violate this continuity. Is that all right? That's why when these two hold together, it's either increasing or decreasing. Is this fine?
Excuse me, ma'am.
Does anyone have? Yes.
Ma'am, what you mean in above examples, what you mean by using definition?
Using definition, which one? This one. So the definition for 1-1 function is, let's just say f(x) is a function. This is the definition. If the function's value is the same as x and y, then your x and y should be same. Is that okay? This is the definition of 1-1 function. Is that okay with whoever asked the doubt?
Yes, ma'am.
Okay. Next up, we have exponential functions. We're quickly going through the properties of. We don't have to. These are very basic properties. The other one is this. And then finally this. And then there are some other properties to this, which are like, first thing is it's a 1-1. Just discuss how it looks like. If you have a to the power x, and where a is greater than 1, it looks like this. And if it's between 0 and 1, suppose 1 is the domain and range of it.
When your voice is lagging very hard.
Is it a problem with everyone here? Should I rejoin?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, I'll rejoin.
Ma'am, you are neither audible nor visible.
She haven't yet joined the class.
Okay, I've joined in, guys, and you need to give me a minute. I'll be sharing my screen. Is it still lagging though? My voice? Like, is it fine now?
Yes, ma'am.
Okay. We were doing this thing. Just 1 second.
Excuse me, ma'am.
Yes, it's fine. The voice is fine right now. Is it fine?
Yes, ma'am. Can we use that using definition method to all questions?
Can't hear you. You'll have to speak a little louder.
Ma'am, can we use that using definition method to all questions?
No, you can't. That's why we have different methods. Sometimes you don't get anything from there.
Okay, ma'am.
Okay. So this is, both of them are one function, and then if we try to check the domain and range of it, so we know that the domain is from minus infinity to infinity. You can substitute anything here. I hope that's not an issue. Everyone understands why we can substitute anything in this function. And then the range is from 0 to infinity. So no matter what your a is, or we can see it from here as well. No matter what your a is, it's obviously going to be a to the power x is always greater for all x and for all a as well. Unless you're not taking something in the, let's just say you're not taking this thing, then though it's not even real. But when it's real, it's obviously positive. So this is it, the basic things about the exponential functions. And let's just say we've already discussed this thing, but we'll just see it one more time here. Let's just say you have something like this. Then this function is, it's half here, it's less than 1, and then it's minus x. We know that half x is a decreasing function, but because it's not half x, it's basically this thing. So this is nothing but 1 by 0.5 to the power x, right? So this is, because this is a decreasing function, so this whole is going to be an increasing. Is that okay?
Yes, ma'am.
Then you have these things where you have the graphs of, let's just say you have to compare the graphs of, this is a totally different graph from all of these, because if you just, let's just not take this one. Something like this. So on the positive side, if we just talk about the positive domain, the bigger base you take here, the lesser value you get. So it will be like this. So if this is it, you'll keep an x here, it will be more like this. It will be less steep. And if you take something like this, so it keeps increasing as you increase this. So as you increase your base, this is likely for 2 to the power x, and then this is for 3 to the power x. If you keep increasing this, you keep getting closer to the y-axis from here. Then on the
Ma'am, but it is different for 0 to 1 domain.
one domain, it's
Ma'am, domain from 0 to 1.
yeah, it's not different here. It's only different when you have this thing in the base. So when you have something like this, and if you take 0 to 1 here, then it's a decreasing thing. But if you have this thing and you take from 0 to 1, it's still increasing. 0 to 1, yeah, if you're talking about the A thing, if A is between 0 to 1, yes, that changes. We're talking about A greater than 1 for now. If you take A to be less than 1, then things will change. So it remains here. Obviously, this every point's y-intercept is the same. So for all of them, the y-intercept is same, but it keeps going. And for the negative side, if you take, so for the negative, it becomes this thing. It becomes exactly the same as A less than 1. For the negative part, it becomes this thing. So if you have to compare these things, so if you increase the powers now, it will just, this thing will decrease. This, it changes here. This becomes the steepest. The steepest one will be this. I mean, the sudden changes will be in this one because it's increasing. So it's increasing the most when your x is positive. And when it's decreasing the most, because 1 by 7 just, if you take the powers of 1 by 7 or compared to 1 by 3, obviously 1 by 7 is going to decrease more rapidly, right? Thus the way 7 increases, when 7 is raised to 1 by 7 is nothing but this, no? So if 7 increases more rapidly than 3 to the power x, then 1 by 7, this thing increases more rapidly than this thing. So if you take, if this is decreasing more rapidly than this, and this whole thing is, no, this is increasing more rapidly than this, then this whole thing is decreasing more rapidly than this. Should I explain this one more time? Or is it fine?
No, miss, draw the graph of this 1 by 2, 1 by 3, and 1 by 7.
The graph is this. When you draw some, the bigger exponent you take here, it's closer to y-axis here, and then it's closer to x-axis. And then if you will take this one, let's just say, so you'll have it like this, and then here you'll have it like this. Is that okay?
Yes, ma'am.
Then if you take this one, it will even be lesser. This, and then it will go up. Is that fine?
Ma'am, please, the 1 by 7 raised to the power x, please explain that again.
Then you have this thing.
7
to
raised
the
to the power x, I understood, ma'am.
Okay, so you understood this part, right? So if you take the reciprocal of this, what I'm trying to say is, if this is greater than this, then isn't this going to be this thing? If this will change, right? This is going to change. Is this fine? So when you come to this side, the one that had the higher value of y, this was bigger than this one. Now it becomes less than this one. Is that okay?
Okay, ma'am.
Okay.
Excuse me, ma'am.
Yes.
Ma'am, if base is same and the value is different, how we are gonna compare here?
Yes.
Like we are
You're
comparing
talking about
7
this
raised
thing?
to the.
This thing?
Yes, ma'am. Yes.
It's an increasing function. No, that's what we discussed. That when you have a to the power x, we discussed it. It's an increasing function for a greater than 1.
No, ma'am. I am saying like if we are asked to compare between these values on the graph, like we are drawing 3 raised to the power x graph and 3
These
raised
two
to the
are
power
the
y
same
graph.
thing. X and y doesn't matter. It's you. If you do 3, you even if you change this is just a variable. It doesn't matter what you keep here. It's the same thing. Is that okay?
How, ma'am, if we put x, y different, the values are different now?
Okay, when you take the function, it's this, right? So if you take it to be this, and if you're taking a particular value, let's just say you're taking x equals to 1, then your function becomes, if you're taking this thing, then they're obviously different. Now it's different. Let's just say you're taking x equals to 1 and y is equals to 2. Now these are two different things. Now you have two different graphs. So this is fx equals to 3 is this graph, y is equals to 3, and this is y is equals to 9. Is that okay? If you were talking about this thing. Otherwise, the variable, if you're taking this as a variable, then it doesn't matter what you take because it's a variable. It doesn't matter what you denote it with. You denote it with t, x, y, doesn't matter. Is that okay?
Okay, ma'am.
Okay.
Thank you, ma'am.
And then one more thing that's there is, I forgot what I was trying to tell. Yeah, I'll just tell you when I remember it again. So, and then you have the compounding formula, this one, where you use the exponents to solve the equation. So this is one more thing that's in week 5. We'll do questions on this later. And the next step you have composition of functions, where we basically discuss about the domain, range, and other things. Basically, these two only.
So, ma'am, this compounding, what you said, are we going to take a look at it later?
Yes, we have a question on this later, I guess.
Sure.
And yep, we have a question on this. At the very end, I have some questions.
Sure.
So we'll discuss it there. Otherwise, it's not a big deal. It's being discussed, but we'll still discuss it at the end.
Sure.
Then composition of function, you have this thing, compose, which just means this thing, simply this thing. So for substituting this gx thing in f. Hope everyone is knows this thing. With quickly going through the composition thing. If your, let's just say your FOG is 1, 1, then can we say that this just means that your G is 1, 1, 2. We're not doing the proof of everything, but it's easier for you, if you do remember these things, it's easier for you to figure out things. So if your FOG is 1, 1, your G is going to be 1, 1, and FOG being 1, 1 does not imply that your F is 1. It's simply because if your G is, let's just say your G is not 1, 1, then you'll have this thing for different X. And if these two things are equal, then these two things are going to be equal as well. So if G is not 1, 1, then FOG is not 1, 1 either. Explanation for this one. But if your FOG is 1, 1, this does not imply that your F is 1, 1. So your F might not be 1, 1, your FOG can still be 1, 1. So one example for it, this basically happens when you have a, let's just say you have e to the power x. And this is, what is this thing?
X.
Okay, so first you need to know the domain of it. If you know the domain of it, domain and everything, then only you can just tell if it's, let's just see this thing, e to the power x is from R to R, right?
Yes, ma'am.
So we're first trying to verify if this is a 1, 1 function or not on every domain. Sometimes the domain doesn't matter, the other times it does. So let's just say you have x1. One one is, I don't think that's a problem. It's more about the ontoness of the function. Just say that you're taking the domain to be R, and then this is it. So what I was trying to say is that you need to know the domain and everything of these functions. Let's just say you take it to, if you're taking it to be this thing, and you're taking this to be from natural log of R plus to R. If you're taking it to be these, this is what you're taking, the domain and codomain stuff, then it is X. Otherwise, if you take, let's just say you take R to be from here, let's just say you take this to be from here to here. And then this is not even defined, isn't it? Because then you'll have e to the power x. So not this one, actually, this one. If you have this thing, so you have natural log of here to here. Okay, just give me a second.
You're saying there could be negative values where you shouldn't have.
Yeah, it's basically what happens is if you take this thing, then it's x only. But if you take, let's just say you take this thing and then you take it to be this. And here you can't take this
Ma'am,
thing.
you take codomain of ln of x wrong.
Yep, problem is that e to the power x, what we were trying to say, that e to the power x is the inverse of natural log of x only when this is, okay, we were talking about the You just phrased it wrong, the question wrong. So e to the power x is the thing is it invertible all the time? This is it. It won't be invertible if you're taking this thing. Codomain is you can't take codomains wrong. You can take ranges wrong. Ranges can be wrong. There are no wrong codomains. You can take codomain to be whatever you want, but the only condition is your range should be in the codomain. That's the only condition on codomain. Otherwise, you can't take codomains wrong. So if e to the power x is this thing, let's just say, if you take e to the power x from here to here, then it's not an invertible function. So firstly, you need to, if this is something here, then you will first need to figure out before stating that it's x. You first need to figure out what's the codomain and domain and everything. Is that okay?
Yes, ma'am.
What happens here is, in this case, you can't compose it outside this. If you take the codomain to be something else, you can't compose these things. That won't be possible. And this is, we don't have an example for this one right now, but this isn't always true because we can still have a look at this using the reasoning that we. So if you take this thing, let's just say you have this as 1 1, it doesn't mean your f is 1 1, because if for your f to be 1 1, we know that your g is 1 1, right? So what you can do is you can just apply FOG to G inverse. So this is what you can do. You can do this thing, and you can do, let's just take y1 here, G inverse of y1. And since your G is 1 1, so if you take, let's just say your gx1 is y1 and gx2 is y2. So take this thing here. Even if you don't take it to be this one, it's still fine. So you'll get f of y1 the same as f of y2. So that is going to happen. Now you will see that your f is from, this turns out to be 1 1, but only on the, it's on the domain of G inverse. All in all, you do get a condition on you have to take y1 from the domain of G inverse, right? Y1 and y2 you've taken from the domain of G1. That's when your fy1 and fy2 might turn out, they'll turn out to be same. But otherwise your f is, okay, then we're doing something wrong here. We were saying that this is a 1 1 function. Let's just say your f is a 1 1 function. Let's just say that this gives you this thing. And your g is a 1 1 function too. And FOG is a 1 1 FOG is a 1 1 function too, right? So it's the, I don't really remember the proofs right now, but there is some inconsistency when we do this thing. And so all in all, this has to be a 1 1 thing. So G has to be 1 1 for F to be, sorry, G has to be an onto thing. So if your G is onto, then we almost got there, no? We discussed why, so if you do this thing, this is not important at all, but we're still discussing it. So if you'll apply this FOG to G inverse of Y and G inverse of X, you get Fy, then you will get Fy1 equals to Fx1. So all in all, you'd want, now this is only true for y in the domain of G inverse, that is y in the range of G. I don't think anybody understand what's going on, so let's just, I'll still do it till we end. This y is, if this is in the domain of G inverse, then it's in the range of G, right? That's how domain and range work in inverse functions. So y is going to be in the range of G. So this is only true for the elements of the elements that are in the range of G. So all we're trying to say here is that this does not imply this. So if anywhere you're given this thing, this logic should not be used. This was the point of all of this. And then we have okay, let's just do an example then. So let's just say you have natural log of x squared plus 1. And you need to check if this is 1, 1 or not. So can anybody tell if this is 1, 1 or not? It's a very simple thing. And it's based on what we've done just now.
It is not.
Yep, it's not. Why is it not?
It basically looks like a quadratic function.
We just discussed it right now. If this is a 1, 1 function, then gx has to be a 1, 1 function. And this is not a 1, 1 function. See. So if this means that if your gx is not 1, 1, then your FOG is not going to be 1, 1.
Okay.
And it's pretty obvious from here. If your gx is, we have discussed this. If this is not 1, 1 for different x1 and x2, if g gives the same value, then if you just apply f here, then f is going to give the same value at different x1 and x2, right? So if g is not 1, 1, FOG, so the thing is that if you're in a function in this, the one that's applied first is not 1, 1, then this whole thing is not 1, 1, no matter how long it is. HO, FOG, or if you have something else, if this is not 1, 1, then this whole thing is not 1.
Excuse me, ma'am.
Yes.
Ma'am, I don't get this point. Please explain this part again.
Okay, we just said that if your G, let's just say your G is not 1, 1, or let's just say your G is 1, 1. G, let's just go. This is what we're discussing. We're saying that if G is not 1, 1, then FOG is not 1. If you have to check if a composition is 1, 1 or not, no matter how long the composition is, let's just say this is a composition. And you know that if this function is not 1, 1, then this whole thing is not 1. Why so? Because if gx1, g being not 1, 1 means that there are x1 and x, there are two elements not equal to each other. So that gx1 and gx2 are same. Right? This is what we mean when we say that gx is not 1. Is that fine? Now, if you apply
Okay,
f on both sides, you'll get FOG x1 equal to FOG x2 when these two elements are different. That means for different elements, you have the same value, this, on x1 and x2, which means FOG is, now if you'll apply something else as well, it is still not 1, 1, right? This thing is also not 1, 1. So keep applying things here, that doesn't matter. That's what I was saying. But if your innermost function is not 1, 1, then this whole thing is not 1, 1 either. So you're in this thing when you have this thing, because this is not 1, 1, because, or what does the graph look like? Let's just keep it simple.
Excuse me, ma'am.
Yes.
Ma'am, the condition you said, I understood that condition. But if it is 1, 1, then f of g, how long it is, doesn't matter.
No, it's, if this thing is 1, 1, then this might not be 1, 1. It's only one way.
Or it's a vice versa also
No,
true or
it's not vice versa. The converse is not true. Converse is not
true. Okay, ma'am. Thank you.
So if you have this thing, what we do here is if you get same value for 1 and -1, so 1 and -1 give the same value here. So natural log of that -1 square and 1 square is going to give you the same thing. No matter what you have, if this function gives you the same thing on different elements, then this whole function is going to give you the same thing on different elements, on those two different elements. I hope that's clear. And then now we'll discuss the range or other things for other parts. So let's do this thing. Let's just have natural log of x. X is this, and g is natural log of square root of x minus 2. Let's just compose these two things. You take FOG, you get uh, natural log of x minus 2. Right? GOF, you will get natural log square root of natural log x minus 2. See this thing. We'll discuss oneness, and then we'll discuss one more thing. If you have both the functions, we will mention this thing. If FOG is there and both f is 1, if f and g are 1, this means that your FOG and GOF, if the composition is possible, is 1, 2. So if you look at this, this is a composition of two 1, functions. So this is going to be 1. Taking square root of a 1, function keeps it a 1, function. You can consider this to be another composition. So this is a composition. You could have considered it the composition of three functions. Root x is also, one of them is root x. And root x is also a 1, function. So it's composition of three functions then. And all of them are 1, 1. That's why this whole thing is 1. Is this okay? Same goes here. Then we'll discuss the domain and range. So if we discuss the domain, let's start with the domain first. Domain of FOG. So you firstly would want square root of x minus 2 to be greater than 0. So for that you would want x to be greater than, it's always greater than 0. So it's a square root, right? Square roots are always greater than 0. So you don't have a restriction on x, but for this to be defined, for square root to be defined, you need x to be greater than 2. So this is one condition on x. And then you want natural log of square root of x minus 2 to be greater than 0. And we've already discussed this. Okay. Log has been, we've not started with log, but log is also an increasing function when it's this, right? So it's an increasing function when your base is greater than 1. And since your base is e here, e is greater than 1. So it's an increasing function. So what you can do here is, or you can just look at it as, just raise both of these to the power e. So you'll have x minus 2 square root greater than e to the power 0, which is 1. So you would want this to be greater than 1. And this to be greater than 1, you would want x minus 2 to be greater than 1, right? And want this to be greater than 3. It's all right. It will have other branch to it too, right?
Ma'am,
That's it. Yes. Is there a doubt?
will this type of question come in exam?
You'll have questions on domains and everything. And it's very important to be at least able to find the domain and range of functions. especially when we are discussing it in continuity and everything, and not
Excuse me,
knowing how
ma'am.
the domain is. Yes,
Ma'am, what you have written there, root x minus 2 is greater than or equal what?
to e to the power 0, and then it's 1. Is it fine?
Ma'am,
Ma'am,
Yes.
how you define that?
How do we define this thing, or how do
Yes,
we get
ma'am.
this thing?
Yes, whole thing.
How do we get this thing from this thing?
Yes, ma'am.
Okay, so what we do here is e to the power x is an increasing function, right? That's what we are discussing. And natural log of x, we just discussed, is an inverse of e to the power x on, we discussed this thing, right? This is an inverse when you take the codomain, which you will take obviously because that's the natural codomain of e to the power x. So the natural codomain of e to the power x is r plus. That's what we'll take. Don't confuse it with the example that we did where we said that if you take it from r to r, that's not the natural codomain of e to the power x. We'll keep it from r to r plus only. So this is the inverse. So I hope you're aware of this thing, that natural log of x and e to the power x are inverses of each other. So if you'll apply this thing here on natural log of square root of x minus 2, then you get square root of x minus 1. Because this is an increasing function, your sign doesn't change here. So if you have x1 greater than x2 and f is an increasing function, then this doesn't change, right? That's what we've done here. We've applied e on both sides. We've raised both of these to the power e, and that's what we get. E to the power natural log of square root of x minus 2 is square root of x minus 2, and e to the power 0 is 1. Is this okay?
Okay, ma'am.
Okay.
ma'am,
Yes.
can you please repeat why FOG is one function?
Which one? What is your question?
Why FOG is one function?
Okay, this one. This we've just written the reason here. It's because if your f is a 1-1 function, g is a 1-1 function, then your f, do you want me to do the, you don't need to do the proofs of everything. You just need to know that if these two functions are 1-1, then your composition is also 1-1. And since this is a composition of all the 1-1 functions, what do you see here? A square root, a natural log, and a square root. And then this function x minus 2. These are the functions. So this is basically a composition of a square root function, a natural log function, and x minus 2 function. So because all of these functions are 1-1 functions, that's why this composition is 1-1. Same is the case with this. Is this okay? Now,
Okay, ma'am.
we're discussing the domain and the range of this. So we are done till this part, right? We have seen there's no restriction on this. Then we get a restriction on this for x to be greater than 2. And then a restriction on this when we consider this thing. We want this to be greater than 0, and this is the second restriction that you get. So we can just simply take this restriction and drop this. This is redundant now. So then you take the square root restriction. So finally, you want natural log of square root of x minus 2 to be greater than 0 because it's in the square root, right? So we'll apply e function. We'll raise this to the power e 2 times. This is e. And by the way, if you have log here, let's just say you have log base 4, then you have log base 5. So you raise it to the power 4 because log base 4 is the inverse of this thing. So if instead you have a log base 4, then you will raise this to the power 4. Is that okay? Okay, then you'll apply it one time, you'll get this thing. If you'll apply it one more time, you'll get e and square root of x minus 2 greater than e. And now you just have to solve this, so you get e square plus 2. That's it. So e square plus 2 is clearly greater than this. E square is 2 point something. So, and the square of it is, so this thing is clearly greater than this thing. So you can just drop this thing and take, you had these conditions. This one, and this one. So this condition is enough, right? So this is the condition on domain. That's how you calculate the conditions on domain and finally find the domain. So it will be this thing. Infinite. Get the range of it, we have a square root here. Get the range of it. So what do you think is going to be the range? We have very less time left. So does anyone know? Or should I do it?
0 to infinity.
Okay, 0 to infinity. Why? How do you know? It makes sense that it's from 0 to infinity because this is a positive thing. But how do you know that every point here is included? How do you know that every point has an x for it such that this thing is that point?
And 3 comma infinity it should be.
Okay, let's just see what it is. What happens is that this is a function. If you just look at it, it's from 0. You have to check which, but there are several ways to do it. One way to do is you can just put this equal to r and see if this there's some x or not. So you get an equate this thing to r. You get natural log of square root of x minus 2 equals r square. Then you get e to the power r square, natural log of. So we can clearly see that we can get an x such that when we substituted the x here, we'll get r here, right? We want this to be equal to, and r is an arbitrary number. So no matter what your r is, positive, negative, 0, you can find an x such that if it's fine, or should I do it?
That's fine.
Everybody understood?
Then what's its domain?
Sorry, what?
What its domain?
Its domain is this thing, if we haven't made a calculation mistake.
Okay then, thank you.
Okay. And the range we're looking for is, let's just say there is any number r, then you can just try to find x such that we're looking for x in terms of r. If you're able to find x in terms of r, then there is an x such that this thing gives you r. That means it's a, now we know that this can't be negative. And also, if you take anything positive here, you will have negative, you can't have because there's a square root here. And then other way could be, there's one more way to it, if which is your natural log function takes all values from, you can just take it this way. So if you have a function, let me just write down this thing. If you have FO, GO, H and everything, and all of these are onto functions, and this is an onto function too. The composition of onto functions is onto, just like one functions. So if you look at this thing, now onto depends on the codomain. So if you take the codomain to be from 0 to infinity, we know that this thing is onto from 0 to, is it natural log we know is, square root we know is, we just have to see this thing. Or what you can simply do is, there's even a better approach to do this thing. These two are a little complicated. Let's just do this thing. We know that this gives us, if you take, we know that this is an increasing function, right? All of these are increasing. square root is an increasing function, natural log is an increasing function. So what you can do here is, when you see an increasing function, you ask the range of it. Let's just say you know the domain, it's AB, and the function is f, and you're asked the range of it, it's simply this. If it's an increasing function, it's this thing, right? And a continuous function too. It should be an increasing function and a continuous function. So this is an increasing function and a continuous function. So you can just, you have the domain is, what did we get as domain? E square plus 2 and
Ma'am,
infinity.
e square plus 2 infinity.
If you put it here, e square plus 2 minus 2, you'll get e square, and then square root is e, and then natural log of e is 1, and then natural log of 1 is 0, and then square root is also 0, right? We're very short on time, so we're not doing everything. This, when you substitute an e square plus 2 here in this function, you will get a 0. And you can't substitute an infinity here, obviously. But if you try to, you can just intuitively look at it. So when you substitute infinity is not a number, but we're just getting an idea if you take the limit to be infinity. So you can take the limit to be infinity. When x tends to infinity, this whole thing tends to infinity. This tends to infinity and everything goes to infinity. So it's an increasing function, starts from 0, goes till infinity. So that means this is the range. And why we are so sure that this is the range? Because this is a continuous function too. So it's not like you started from 0 and then you dropped something in between and then you continue till infinity. You can't drop things because it's a continuous function. Is that all right? Range, you most probably wouldn't be asked range of such complicated things. But domain, you at least should know. Even if you're asked domain range of such things, this is one way. These are the ways and tricks to do it. Is that all right?
Yes, ma'am.
We're taking up one more thing from here, which is this. Do you think this is a 1-1 function? We'll talk about the domain in a while, but first let's just discuss if it's a 1-1 function or not.
Yes, ma'am, it is.
Why is it a 1-1 function?
Ma'am, because it is in decreasing. No, sorry, ma'am, increasing graph.
Okay, this is 5 minus x, which is increasing, decreasing, whatever it is. So if this is increasing, say, so we just know that this is clearly composition of the same function several times, right? Can you see that? This is the same function composed several times. So if somehow you are able to see that your f is a 1-1 function, then the composition is going to be 1. So if you are sure that this is a 1-1 function, then this is 1-1 as well, right? So is this a 1-1? This is only one branch. So when you have square root things, so either it's this thing or it's this thing or it's some other branch. So it's a 1-1 thing, right? That's why this is a 1-1 function. Is it
Yes,
all right?
ma'am.
Okay, and finally, we're on to the inverse functions. Inverse functions are big. So G is inverse of F if FOG and GOF both give you this thing. If this is true from both compositions, then this is the G is the inverse of F and F is the inverse of G. That's the basic definition, and then we have some properties of inverses which we have already discussed. But let's just discuss them. A function X is inverse.
Ma'am, I have a doubt. Ma'am?
Can you hear me?
Yeah, ma'am. I can't hear you right now, ma'am.
Okay, am I
We can't
audible now?
also hear you. Yes, ma'am, now you are.
Okay, out. Am I not audible?
Yeah, ma'am, you're not audible
No, ma'am,
in
you are
between.
lagging.
Okay, I think it will be fixed. You can just go ahead with your question.
Yeah, ma'am. So, like, we have some results, like, as you said, if we have an square root, we can directly say that it's a one-one function. What else?
Yeah.
Like, what are other results do we have like that so that we can just see and say it as a one-one function?
One thing is when you have compositions, that's what you have basically. So when you have a composition of a lot of functions and all of them are one-one functions, then it's a one-one function. And then if you have the innermost function as we've discussed all these things, and then that's why the graphing helps a lot. So if you know the basic graphs of like x square and then quadratic things and then e to the power x and natural log, because that's what you compose most, right? So if you know the graphs of all of these, you'd know if it's a one-one function or not. A square root of x is a one-one function because it looks like this. So it's a one-one function. So
Okay, so the
graphically, you can
graphs
tell.
help.
Yeah,
Okay, ma'am.
graphs help a lot. So you should remember some basic graphs. Okay. Then if you have a function, uh, is it fine now? Is
Yes, ma'am.
if you have any more doubts from here?
No, ma'am.
Okay.
No doubt.
So if you have a function, say f and f inverse, and this symmetric about y-axis, what does it mean to be symmetric about y-axis? So if this is your thing, it just means that uh, if this is it, then it's just, so consider this to be a mirror. Now, if this is a mirror placed here, then this is going to be the image here. That's what it means. It's exactly this thing, the copy of this thing here. And this is f. So one will be f and other one will be f. That's how your graphs look. So if you have to plot the graph of things like that, you can do it in this way. And if you have the intersection of, let's just say, intersection of f and f inverse, if you have to find out, or there are other things, then the intersection of these two graphs lie on y is equals to x line. Intersection of f and f inverse lies on y is equals to x. So they're symmetric about this, and the point where they intersect. So if they were to intersect somewhere, they'll intersect on this line only. So that point will lie on y is equals to x as well. These are two things about the inverse function. And then you know how to find the inverse of functions, right? We're not doing questions from there. We're moving to week 6 now. Does anyone have any questions from the inverse thing?
No, ma'am, no doubt.
Okay. So we'll discuss week 6 now. Week 6 is basically log and its properties, and that's what it revolves around. So everyone just knows this is the graph of log base ax, and this is, take the inverse of it, it will be, for a greater than 1. Then e to the power x is the inverse of e. Inverse of a to the power x. Have this thing, have it like this. In case you even forget the graphs or something, you can, if you remember all these things, you can just try to figure out what can be the graph, because this is the inverse of a to the power x when a is less than 1. So if you know that the a to the power x's graph looks like this is y is equals to x, and a to the power x's graph looks like
When you are not audible right now.
okay, wait. Am I audible now?
Yes,
Yes.
Log as e to the power x is a 1-1 function. So if you have to discuss it, let's just go to the properties that you usually use. And log is a 1-1 function. So everything, if it's involved in compositions and everything, so you can check if the composition is 1-1 using this. It's a 1-1 function, and it's increasing or decreasing depending on what a you take. So if it's a greater than, then it's an increasing function. If a is less than 1, it's a decreasing function. The same way as e to the power x. Is that okay? So and you can even check it. It's it's the mirror image of, because they're inverses of each other, so they are the mirror image of each other. I've not drawn it the right way, but they are mirror images of each other along this y is equals to x. Then there are some properties of log. First one is this basic properties. Then there is one for multiplication, and then the power one. You can only use it with the same base. Be careful of the bases. And then we have this where you can change the base. So you can change something to C and then do this. Another property. Maybe you can just write it as 1 by log. These are some properties, and then this thing, so you get 0. So what this means is what should be raised to the power a such that you get this thing here. This is what it means, right? So this is it. And then log a is 1. And then if you remember all these things, you're good to go with the questions on logs. So you don't need to know anything else. Just the graphs and then these properties. All the other properties are like used from here only, if there are any to be used. And then we have the domain range thing for log again. So domain is obviously 0 to infinity, and range is from minus infinity. Right? You can even see it there. Then let's just do some questions without indulging into the theory much. So let's just say you have this thing, log base 4 and 2x squared minus 5x plus 6. And you need to solve for x. So what you can do is you can just bring it down. And then this is nothing but 2. And then you can solve this equation. This is a quadratic equation. And you can solve this. This is one type. And then you have, you're not solving it, it's fine, right? You can solve the quadratic equations. And then let's just say you have this thing. And you need to find the domain of this. Okay. So what do we do here? First thing we make sure is x squared minus 6x plus 10 is greater than 0, right? So this is if you, the graphs help you is, we know that when you must have done it in the earlier weeks, when you have a positive a here, this is an upward parabola, right? So you'll have something here, and then so it will be something like this. Not exactly this, it could be somewhere else too, but it's mostly like this only. It opens up. So if you'll have two roots here, then from this root to this root, it's a negative function. Otherwise, it's positive. That's what you need to do, right? That's how graphs help. If you know the graph, you can just know that from this root to this root, this is going to be a negative function. Otherwise, it's positive. So let's just find the roots of this. We're not solving these things. Do you want me to solve it or just tell you how the questions are done? Because solving might take a lot of time.
Ma'am, in the above question, how did log 2 base 4 become 2?
This one?
Yes, ma'am.
Okay, it's half actually. Thank you. Now in this one, you can just find, so I'll need a response on this. Do you want me to solve the questions or just tell you how they're done?
No, ma'am, we can do it.
Okay. So all you need to do is just find the roots because this is a quadratic, this is a quadratic equation. It represents a parabola. So this is, I hope you understood the 2 points that you will get to where you get 0. So x, let's just say at x equals to AB, your fx, your fa and fb is 0. These two if are roots, then from A to B is the problem, but from minus infinity to A and B to infinity, you can use then for these, if you take x from here, this will be greater than 0. Is that all right?
Ma'am, last thing you said, can you please, my network was little bad. Not complete question, the last part you said.
Which one? This one or the previous one?
Ma'am, this one, the last line you said, my phone was not working properly.
If the roots of this equation are say A and B, that means for x equals to A and B, your function is 0. That means this is the point A0 and this is the point B0, right? So graph passes through these 2 points. That's what it means. And since it's an upward parabola, this is the possible case. So that's how your graph mostly looks like. So from A to B, you're going to have the value negative, and from here to here, it is positive. And you want this to be positive. That means it's from minus infinity to A, B to A. Is this clear?
Yes, ma'am.
I think this particular example, I think the equation is doesn't have any roots. So it's above the
So if it's not, if it does not have a root, then it's basically above this thing.
Okay.
If it doesn't have a root, then it's completely above the x bar. It can't be below it because that's not possible.
So that's safe, no? Then that means like all of R can.
Yeah, that means all your part is positive. Because you can't have anything. If you have negative, then it will have to be 0 somewhere. If it is negative and if it is positive, then it has to be 0 somewhere. It's a continuous function, right? And then log part, you already know how to do it. So let's just say you've got this to be the domain. So this is greater than 0. And then you want this thing to be greater than 0, right? So you want log base 2 x square minus 6x plus 10 to be greater than 0. So again, let's just take e to the power. Let's just raise both of them to the power 2. It doesn't matter here because we have a 0 here. So we're going to have 1 and this thing. We want this thing to be true, and now you need to do the same with this equation that you did with this. Is that okay?
Okay.
Okay. And
You
then
did
you're done.
2 raised to 0 on the inequality side.
Raise both of these to the power 2. 2 to the power this and 2 to the power 0.
Okay.
And you can do this, and when you have we have a 2 here, so it's a nice thing. If you have log half instead, then your inequality is going to change.
Okay.
Please be careful of it. So change
Ma'am,
the
I
thing.
have a doubt from grade assignment week 8. Can you clear that?
Week 8, we have a revision section for week 8 tomorrow. And to be honest, we're left with a lot of parts from week 6. A lot of questions from there that I have to discuss. Let's just do the week 8. You can discuss week 8 tomorrow.
Excuse me, ma'am.
This is how you find it here. Yes. Yeah, next. Yes.
Ma'am, just please discuss one thing. Sin x by x. Can you please check differentiability on this? Just one doubt.
We have see, we're only left with some minutes, and there are other questions, and there are questions from this week. The log one especially.
No, ma'am,
So,
just one example. Sin x by
okay,
x
sin x by
differentiable.
x. You want to check the differentiability of it. So what you do here
Yes.
is sin x plus h. Let's just go by the very basic definition of it. And x plus h minus sin x by x tends to 0. Have sin okay, it's getting 0. It's what's the domain of this function?
Ma'am, it is not given, just we are given sin x by x and we have to check differentiability. If it is x greater than equal to 0, it's like that we are
You
given
have been
fx.
given the domain, right? It can't be greater than equal to because you can't substitute a 0 here. So if this is the
Yes.
function, this should be the domain then. Okay. So if you'll take the other parts of it, it is different. What is the problem here then? It's differentiable, no? Because you might not be able to find this limit, but it's sin x is a differentiable function, x is a differentiable function, and then by the
Ma'am, it will
algebra.
be x according to me. Sin x by x is equal to x for any value.
What? Sorry.
Answer of this question will be x according to me.
Answer of this, do you need to find the derivative of this, or you're just ask the differentiability? If it's about if it's just about the differentiability, then this is a differentiable function because it's uh, the 0 is not included here, so you don't have to. The only point that might trouble you is 0, and it's not in the domain. And for differentiability, you need the point to be in the domain. We discussed this in the other section. Fine. Let me move on to the question that we were doing.
I will ask it again, ma'am. No problem. You can continue. It's getting late.
This is a differentiable function because your domain is this thing. If it's just this function, then it is differentiable because both of these are differentiable functions.
Okay, ma'am.
Okay.
Thank you, ma'am.
And let's just have a look at this one. You have this is a change of base question where you need to change the base. So if you change it, you'll have log base 2 x square minus 5x plus 6. And then this is simply log base 2x minus 2 equals 1. So you can have log base 2 here, this thing here, and you can just take this thing here, log base 2x minus 2. And then just, because this is a 1, 1 function, now this is where these things help. So log is either you remember the log is a 1-1 function or you just remember the graph of it. So you can see that it's a 1-1 function here. This is a 1-1 function. So that means you can just equate these two things and solve it. Is it okay? All you have to do is just the calculation part. Let's just have another question like this one. Just you have this thing. So you have minus. We know what this thing is. This thing we don't know what this is. So when we say we don't know what this is, we mean we don't know how this function works. You don't know anything about this function, but you know everything about this one. So let's just change this one then. Or because 81 is okay. And one more thing, if you have log, let's just say you have b cube a here. So what you can do is this means and let's just say this is n. So this means b cube n is a, right? If you take 1 by 3 on both sides, you will get b to the power n is equal to a 1 by 3. It would mean that your log, if you will just take base b here, you'll have to take 1 by 3. And so these two things are same. All I'm trying to say is you can take the 3 and remove it from here and take it here as 1 by 3. Is that okay? That's also one of the properties that you can see from here. So you will have this thing, which will be, let's just say 3 to the power 4. This is 4 minus log base 3x. Change this thing. Could have changed the other way around as well. You could have changed this instant, but then you'll have to deal with this property. Then you'll have 4 log base 3x. Oh, minus 1, and this is log what you can do is you can substitute log make this thing to y. This will be 4y square is equal to 4y minus 1. And then solve for y. And let's just say you get the value of y here, put it here. If it's a negative thing, then discard that one. If y is say minus 2 and minus and 1, so consider only 1. Minus 2 is to be discarded because log cannot have a negative value. So then you just find the value of x in terms of y because you already know y. Raise it to the power 10. Or raise it to the power x. Base is x, right? So you will have 3 here and x to the power 5 here. Let's just say you have 1 or let's just say you have 2 here. So you will have this thing. Is that okay? Let's write it down. If you have this thing, let's just say this thing is 3. And you have 3 here. That means if you raise this, you'll get a 3. So you can then just take the cube root of both and get the solution. Is this fine? Is this fine? Am I audible?
Yes, ma'am.
Okay.
Ma'am.
And then let's just try some questions more. Let's just say you have to find the maximum value of this thing. Now, one way to do again is using the derivatives to find the maximum value. And the other way is you can try to make some modifications here, like this one. Log, you can write it as x square, which is very, see, this is a complicated process. This one is a little complicated if you this, because it's not very intuitive that you can write it as this and then you can write it as 1 by 3 log x. Calculation that we've done here in the question is not very obvious. So you might not be able to think of something like that always, but if you are able to, then you can just avoid using the derivatives. So this is an increasing function. So this complete thing is a decreasing function and this thing is a decreasing function too. So if this is increasing, your 1 plus 3 by your x, if it increases, this thing decreases, right? And this log is with base 10, which is an increasing function. That means this whole thing increases. If the argument increases, then this whole thing increases. Log of this increases. That means it's an increasing function. So if you have to find the maximum of it, this is decreasing, increasing, this thing is decreasing. Okay, this is increasing, this thing is decreasing, so this whole thing is decreasing. And log is a increasing function, right? So this is decreasing. Is this part clear?
No, ma'am. If x, please, can I ask question?
Yes.
Ma'am, here if x square plus 1 increasing, then 3 by x square plus 1 complete
For
value
x,
decrease.
there are some conditions on it. When you say x square plus 1 is increasing, it's basically increasing, but because it's a quad, again, something like this. So it's not always increasing, but uh, after a certain stage, it's increasing. And yes, what were you saying?
Ma'am, it will increase now the x square.
Yes, this x square will increase in a particular domain, and that, let's just say we are taking the domain to be that particular domain. So if this thing is increasing, this thing is increasing, this denominator increases. So if your denominator increases, the whole thing decreases. That means this is also decreasing.
And then you're saying the log function
Is
is
also
decreasing.
yes. Log function is increasing, but this thing is going to decrease. So when log function goes with this, so if this is the argument of log function and this goes up, this increases, then log function also increases. If this decreases, log function also decreases.
Till the certain value, na, it will increase, like we put x square in its domain.
Sorry, what?
It will increase to the but certain value, as you said, x square in the domain, the value of x.
Yes, because the problem is here, not in this. In this logic, there is no problem. The problem is here because x square plus 1 is not always an increasing function.
Okay.
But we are taking x tending to what we're interested in is we want to find the maximum value, right? So we want to find the maximum of this. If we want to find the maximum of this thing, this will be attained when, okay, if this is a function, let's just say this log is a thing, then your log and you have fx. So you want to find the maximum of this thing. So you can just find the maximum of fx and then find the maximum of fx and then just let's just say it is this fx1 and then substitute it in this because log is an increasing function. Is this thing clear to everyone?
Yes, ma'am. Can you please check the maximum value on the given example?
Okay, so this is,
it should be 4 now.
Yes, it's 4.
Okay, ma'am.
Okay, it's log 4 basically. because then you'll apply log, right? The maximum of this is 4, but then you apply log, so it becomes log 4. Is that okay?
Okay, ma'am.
Okay. And then we have another thing, this one. I had other questions too, but we're not left with time, but we'll do one or two of them too. So this is it. So you can just write it as 5x. If you have to solve this thing, you can just write it as 5x, 5x into 5 and 5x 25, and then substitute this as y. You don't even have to substitute it. You can simply just get 25 plus 5 plus 1. It is 31, 5 to the power equals this, and then you can just solve this. Then we have some questions here. So for someone wanted to discuss these questions, right? These type of questions. Let's just start with this one. This one in particular. Let's just say number of bacteria after T hours is given by this equation, and where B naught is the initial count and K is a positive constant. If the population grows from 2,000 to 32,000 in 3 hours, the time given is 3 hours. And this equation also uses the unit as R. There's no problem. Then your B naught is 2,000. Find the time it will take to reach this. And your B at 3 is given to be 32,000. So first what we do is we substitute everything here and find the value of K. So B3 is B0 4 K3, and then we find the value of, because we know the value of everything, right? We know what this is, we know what this is. So this is 32,000. Then this is 2,000. This is 4, 3, K. Now you need to solve this equation. So you will get a 4, 3, K. You know that it's 3K is 2. If you have any doubt in this, you can just ask. So K is 2 by 3. And then we have the complete equation here. So your equation actually is this. B naught 4 2 by 3 T. And now you need to find the time T it will take to reach this many bacteria. So it's 1 to 8, and then this. P naught you already know, 4 2 by 3 T. Just solve for T. Is this clear to everyone? If other questions too, I need a quick response.
Yeah, ma'am, clear.
Okay. Then just have a look at this one. This one is again very easy. So it's, and you have done similar type of questions. Just have a look at this question and tell me if there is a doubt. We should discuss it or not. Otherwise, we'll move to the next. Okay, let's just do it. So, compounding formula is this, right? Mostly be given this formula, but you should know what these things are. So this is the formula where n is the number of times you compounded and this is monthly compounding, so where n is 20. You can just take 1200. R is 16. 1 is 10. And then your T is 1. No, T you need to find, right? 12T. It grows 25 times. That means it's 25 times of 10. This will get cancelled. And you just need to solve for T there. Is this all right? Then we move to the next one.
Ma'am, can you repeat?
This one, this is the principal amount A. This is, are you clear with this formula? Because if you know this formula, it's extremely simple question. This is the principal amount. This is 1, this is the rate of interest, this is the number of times you do compounding in a year. So it's a monthly compounding, so it will be 12. Every month the money compounds, right? So it's 12 in a year. 12 times it's compounded in a year. And then R is given to be 16. And in the end, they say how much time would it take for it to become 25 times of the initial amount, the principal amount. This is it. And you don't even need to know the principal. By the way, this information is redundant here. You don't need it. Is this okay?
Yes, ma'am.
The one 50,000 a plan that compounds annually at 6%. So again, the P or A you call is given to be 50K and the R is given to be 6. However, due to a holding restriction, interest starts. So till 3 years, you don't get any interest. And let 8 be the amount in account after 3 years, which of the following is correct. So this is if this restriction was not there, this would be the answer, right? Because you have 50,000 and 1 plus R, which is given to be 6 by 100, and then T, and it's annual compounding, so your N is 1 here. Your N is taken to be 1 here. In annual compounding, it's 1. Compounding is only done one time here. This is it. So this would have been the answer if this restriction was not there, but it's there. So this is not the answer. So it says that for till 3 years you don't get anything, no interest on the principal amount. So it's this for t less than 3, right? So if you take t to be less than 3, so if you just deposit it for less than 3 years, then you don't get anything. You just get your money because that's a holding restriction. And then after that, if you take t to be greater than 3, so after 3 years, as this one suggests, this becomes it. But what you need to change here is because it's after. Okay, after t years, after, so you will have, so your t here will be, it will start from, it's like this, 1 year, 2 year, 3 year, you don't get anything. And then your t starts from here. This is your 4th year is t is equals to 1. 5th year is t is equals to 2. What you're doing here is you're subtracting 3 from the original t to get this t. Yeah. Is this fine? Is this thing clear?
Then why subtracting? We can directly
Yes,
take
ma'am.
t for t greater than 0. We are applying condition and then subtracting 2.
No, the thing is that yes, you can take t minus 3, but t is the number of years here. So you can't take it to be, if you take t to be greater than 0, that means your first year. So this t here, it represents the number of years. So till 3rd year, you don't get anything. So you can't do this thing.
Okay, you mean we are just subtracting individually 3 years and just calculating the compound interest?
Yeah, 1, 2, 3 year, you don't get anything. And then from the 4th year, you get the interest. So this is supposed to be the first year. Let me just say that this is capital T. So your capital T is the first year here. Is this okay? Because your
Yes, ma'am.
compounding actually starts from here, from the 4th year. You don't get anything from till the first 3 years. Is this clear to everyone? Lastly, we're doing this thing. So let's just say you have something modeled as this. It's efficiency score of a machine in a factory. And then for each month, K is the month number and this is the efficiency score of the machine. So you need to find out if your EK is an increasing function or is it a decreasing function or what it is. So let's just have a look at this thing. and plus 1, 1. Take this to be 1 by 4. This thing is 1 by 4. Log change it from here if that helps. That was 0.1 by log 0.25 and k plus 1. Have this thing. And need to find if this is an increasing function or decreasing. So this thing is increasing. And then look at this thing. So this is your base is this. So this is a decreasing thing, right? Your base is less than 1. So this is decreasing. This function is decreasing. And the reciprocal of it is increasing. And then there is a negative sign. So it's decreasing again. This thing with the negative sign is decreasing. But let's just have a look at this. This is k plus 2 and this is k plus 1. This is increasing. This is a decreasing function. Increasing, decreasing. Okay, this is decreasing. But your k plus multiplication with this thing is increasing. This is an increasing function. What you can do here is you can just check that which one this thing makes it decreasing and this thing makes it increasing, right? So again, now if you know how graphs work, this is your log x graph, and this is your this thing graph. Even if you take it to be k plus 2, it's always greater than this thing. You can test it. If you don't want to do it this way, you can use some other logic. You can just do the derivative of this thing. But so when you do the derivative of this, you see that that's why the derivative is important here. Otherwise, you'll have to use the graph knowledge here. So the derivative of this, and then you will see that it's an increasing function. So even though this is making it decreasing, it looks like it's making this factor is making it decreasing, but this one is the dominant factor. If you take the derivative, you know that this thing is making this function increasing. This whole thing. So wait. Or you can look, you don't even have to get into so much stress. You can just directly take the derivative of this thing. You can just directly take the derivative of everything and then you can see that this is basically this is an increasing function. This is an increasing function. Just give it a try and then because you want me to do it here or can we just move to the next options?
Ma'am, how k plus 2 is dominating denominator?
Okay. This is your final expression that we're getting here, right? 0.5. Just forget about the dominating factor here. You just take the derivative of this thing. Is that okay? Let's just try it. this is 1 by it. What we'll do here is, because when you take 2 here, each time you need to take a natural log 2. So if you take natural base 2 here, you'll have to divide it, multiply the derivative with natural log of 2. So to avoid it, what we do is, because this thing is basically natural log of k plus 1 by natural log of 2. So you'll have this extra thing here each time. So to avoid this thing, because the behavior of log base a when a is greater than 0 remains same. So you can take it to be, for simplicity, if you just have to figure out if it's increasing or decreasing. I'm just telling you this so that you don't have to do all the calculations there. If you do it, then you'll write it as this. Or if you take the derivative of this thing, it will include natural log of 2 in the denominator. Right? This will be 1 by k plus 1 natural log of 2. So this natural log of 2 then will trouble you in the calculations. This can be avoided. You can just simply take natural log here, because they have the same behavior. So it will be 1 by k plus 1 minus then the derivative of this. So it's log 0.25 k plus 1 and k, and then k plus 2.
Ma'am, can you take my doubt?
Yep, it's just the derivative thing. Do this one the derivative bit. Yes, what's your doubt?
Ma'am, I shared the question in chat.
Okay. It will be better if you just dictate it, because wait, bird is flying along the straight line 2y. Okay, when I try writing it, it just disappears. Just dictate the question to me. 2y minus 3x, what is it?
Yes, ma'am, I'll dictate. Question is, a bird is flying along the straight line 2y minus 6x is equals to 6. After some time, an aeroplane also follows the straight line path with the slope of 2 and passes through the point 4, 8. Let alpha beta be the point where
Can you repeat the aeroplane part again?
aeroplane also follows the straight line path,
Okay.
slope of 2 and passes through the point 4, 8.
What slope of dictate the exact question. This is the path that the bird is following, and then what's the aeroplane thing?
Ma'am, aeroplane slope is 2 and passes to the point
No,
4.
don't tell me the slope. Tell me the exact question that's written.
Oh, okay. Let alpha beta be the point where the bird and the aeroplane can
No.
collide. Find
Start
the value.
from after this equation that's given. Start from there. The aeroplane one, start from there.
Okay. After some time, an aeroplane follows straight line path, slope of 2, passes to the point 48. Let alpha beta be the point where the bird and aeroplane can collide. Then find the value of alpha plus beta.
Alpha, beta, what points?
Let alpha be the point, ma'am, where the aeroplane and the bird collide.
Okay, fair enough. So this equation is already given. Okay, let's just say this is the path of it's a straight line. It's the path the bird is following, and then you find this is also a straight line. Let's just say this is this. You need to find the point of intersection of these two lines. What's the difficulty here? You already have the equation of this. You have been given the passing point, so it's it's y minus 8 and x minus 4. Right? And then the slope is given to be. Solve this thing, you'll get the equation for the aeroplane's path, and then this is the bird's path, and then just find the intersection of these two by equating. Let's just say this is y is equals to, find y in terms of x. and then y in terms of x, and then equate these two y's. Is that okay? Or should I
Yes,
do it?
ma'am.
Can you do it now?
Yes, ma'am. Then we have when we were able to find the collision point.
Yes, that will be the collision point x, y. And then you just add these two.
Okay, ma'am. Thank you, ma'am.
Okay. Anything else that anyone wants to discuss?
Yes, ma'am. The previous question that you're explaining, the increasing ln of 2, that one.
Okay. So that one, right? Is it still there? Can okay, it was here. This one, right? What you do here is you just take the derivative of this. And then if, as far as I remember, the answer to this is strictly increasing function. If you do the graph analysis thing, it might take some time. Only do it when you're not allowed to use or when you're not supposed to use the derivative approach. So if it's in, is that all right? You just need to find the derivative of this thing. Shall we do it here?
Yes, ma'am.
Okay. 1 by k plus 1. And then we have, we're taking, okay, let's just keep how it is. Let's just not change things here. 1 by k plus 1. Then natural log of minus, this is minus as it is.
And base will change now.
Which one? We haven't done anything with the base. We just kept this one as it is and taken the derivative of this. And now we're keeping this as it is and taking the derivative of this. So it's
No, when we are taking denominator in numerator,
what? This will be it. Now we need to find if this is positive or not. Doesn't look like it's always positive. Try solving it further. Natural log of k plus 1 squared. Natural log of cancels from there. Plus 1. Natural log of k plus 1 minus k plus 2. K plus 1. I don't think we are going to get anything. Not simplifying. Okay, then
Ma'am, we can do it tomorrow.
Yeah, we can do it. This simplification needs to be, this needs to be more simplified. Can this is this is an increasing function. This is increasing, and this is, have a look at this one. Log
Ma'am, at the last, have you applied, changed the base formula?
Yes, this is the, we change the, we interchange these two. But it's not working. I think then it's neither of these two. It's not increasing and it's not decreasing either.
Ma'am, we can write 0.25 as 4 raised to power minus 2, then minus minus will cancel each other and become positive.
0.25 we can write only as 1/4. And
Ma'am, 4 raised to power minus 2, 2 raised to power minus 2.
yeah, 2 raised to power minus 2, and then you can take minus 2 here. Then here.
Then minus minus will cancel each other.
But then it's the same thing. No, you have done 2 here. Now what happens is this becomes positive and this becomes 2. So now this
No,
is an
ma'am,
increasing function. So
we can
this
keep it
whole
in
thing is
numerator
again
only.
decreasing. But you're saying that you can just change the base here, right? To 2.
No, we can just keep it in numerator. Then value will be smaller, but it will be always positive.
This will become 2 and this. And your 2 is, you had a minus 2 power here. So you have 2 to the power minus 2. So this becomes, if you have 1, what we can do here is we have a 1/4 here, right? We can do 1 here. Oh, sorry. And write it as 3 power minus 2. Will go here, minus 2 power. Remove here, keep it here. It becomes k plus 2. And when you take it here, it becomes 1 minus 1 by 2. So it becomes the reciprocal. So it will become minus 1 by 2 here. So over 2 here, k plus 1 here, and minus half here.
Ma'am, if we did reciprocal, then why minus 1 by 2 remain?
When you have log a, b, let's just say a to the power 3b is equals to something. And if you want to, let's just say x, this means that a to the power 3x is b. So we've discussed it, no? It's so the power x is b 1 by 3. So the 3, if you want to remove from here, it will be 1 by 3 here. If you want to remove minus 2 power from here, it will be 1 by minus 1 by 2 here. In this, then base 2, k plus 1, and then side k plus log base plus. I don't think anything has changed because you've just changed the basis. So it this one is an increasing function now. So this and this is an increasing function. So what you can do is you can try to test it, not taking the derivative of everything here, but you can try taking the derivative of this one at least, and then or I don't think you even need that. Was the question originally though? An increasing or a decreasing function, right? We know that this part is obviously increasing. We just need to find out if the minus of this thing is increasing as well. So let's just take the derivative of only this thing. Instead of we can remove 2 as well because constants don't play any role in increasing, decreasing. So you get this thing with a negative, and then you can use the derivative, I think. K plus 1 log base 2 k plus 1, a negative sign here, a negative again. Let's just drop the negative, it's creating confusion. We're taking the derivative of just this thing, then 1, and minus k plus 2. The derivative of this is this. And this thing, the negative sign, so you get this thing. Right? So this we know is positive. We just have to check this thing. So this is k plus 2, k plus 1, natural log of 2 minus log base 2, k plus 1. And let's just check for the numbers that are there. We have k is equals to keep things simple because we don't really need to know what's happening at the non-integer things, the non-natural number things. So we'll take it from 1 to 12, and then you can just check it. Keep a 1 here, you'll get log 2, which is 1, and 2 if you keep here, sorry, 1, you'll get 3 by 2 natural log of 2. So it'll be tedious You'll have to calculate everything, and then if they all turn out to be greater than zero, then this would mean that this thing is an increasing thing, right? This thing is an increasing thing. This we already know is increasing. This would mean that this whole thing together is an increasing. Is that okay? Is it okay now?
Yes, ma'am.
Okay.
Excuse me,
And then, yes.
in the week 8 graded assignment, there was one question. I think that means that was already checked, but I think that answer they have given wrong. So can you please check?
Which one?
Week 8 graded assignment.
Which question?
Yes, ma'am, I'm telling just. Ma'am, it's question 19. Um, Means they have
Okay,
given
so
a piecewise defined function and they have told that it is continuous and we have to find the value of the
can
m
you
and all
tell
this.
me the function?
It is 3mx plus n for x less than 1 and 11 for x equal to 1 and 5mx plus 2n for x less than greater than 1.
What's the question?
We have to find the value of m plus n given that it's continuous.
It's given to be continuous, right? So this is the only problem is that x equals to 1. Everywhere else it's you're saying the answer is given wrong. What's the answer
The actual answer should be minus 11, but they have given the answer should be 5.
They've given 5. Okay.
Yes.
When x equals to 1, you need to check. So if you just put a 1 here, it's at x equals to 1, the value is this. From here, you'll get 3m plus n. And from here, you'll get 5m plus 2. So you have two equations now to solve. Six, seven, plus n equals 7. And less than minus 22. Minus 11, right? What's the problem?
According to us, the answer should be minus 11, but and we have written that, but after the checking of the answers, they have given that our answer is wrong. It should be 5.
Okay. Just
In that case, we should be given.
not made a mistake there, right? In the calculations.
I have checked with the ChatGPT. It said that if there will be 5mx minus 2n in the second part, we will get the answer 5. So there is a printing mistake in the question.
Yeah, which one? 5mx plus 2n. Which
If
part needs to be changed?
would have been 5mx minus 2n, then the answer would have come 5.
Okay. So that would have been a printing mistake then.
In that case, we won't be getting marks for this question because they are part of
You'll
the.
be getting if the question's wrong, then you'll be getting marks there.
Okay, ma'am.
So
Because it will be affecting our grades. That is why I.
I'll check. Okay, then we're done with today's class. If there are no doubts, then we'll end it here. Okay. Bye all.
Thank you.
Mhm.